Hello, everyone, and welcome to the podcast of the Korean Society for Philosophy of Science. I'm your host, Seungil at Hankuk University of Foreign Studies. For today's episode, we have David Albert, the Frederick E. Woodbridge Professor of Philosophy at Columbia University. As you probably know, Professor Albert is one of the world's leading philosophers of physics. He has written some wonderful books, including Quantum Mechanics and Experience, Time and Chance, Astrophysics, and most recently, a guest at the Riddle. These and other writings of his are part of what has shaped the field for more than 30 years. Now, let me tell you a little bit about the context in which this conversation, this interview, took place. This year, 2026, marks 100 years of quantum mechanics, or at least 100 years since Schrödinger wrote down his famous equation, the Schrödinger equation. So, our society held its annual conference on the philosophy of quantum mechanics, and Professor Albert flew over to South Korea as our keynote speaker. And after the talk, he generously sat down with me for this interview, which I really appreciate. He talked about the realist interpretations of quantum mechanics, his long-running research program on the arrow of time, and a couple of other things too. I really enjoyed it, and I hope you enjoy it too. Professor Albert, thank you so much for joining us. You must be really tired after all the long
Glad to be here.
Yeah, so I have a handful of questions, some from me and some from my students, and I'll try to keep them brief. Okay. Can you begin by talking about the philosophical questions occupying you these days?
I have for a long time been interested in two big questions. One has to do with the foundations of quantum mechanics, and in particular with various attempts to solve the measurement problem in quantum mechanics, or to put it another way, to see if scientific realism can be maintained in the face of quantum mechanics. So I've been occupied with that question for many, many years. It's led in various different directions. We now have some realistic solutions to the measurement problem on the table, or at least preliminary realistic solutions on the table. But those then pose other kinds of philosophical questions. These solutions seem to require that we figure out what the metaphysical status of the quantum mechanical wave function is. That's a question that's preoccupied me for a number of years now. And then there's a whole other set of questions having to do with the direction of time, and with the foundations of statistical mechanics. And I've been engaged in a project for many years that lots of other people are engaged in too, of trying to see whether there is a thoroughly naturalistic account of the difference between the past and the future, more particularly to see whether there's what I would call a thoroughly mechanical account available of the difference between past and future. A mechanical account as opposed to, say, an account where one sees the difference between the past and the future as built into the fundamental metaphysical structure of the world, or other accounts where one sees the difference between past and future as a matter of the first person perspective of agents or something like that. I've been interested in trying to avoid both of those and trying to see if physics has the resources to give a satisfactory account of the difference between past and future.
I see. Speaking of quantum mechanics, among the so-called realist interpretations of quantum mechanics, which do you think is the most promising one? and why? Or to put it simply, is there any favorite?
I don't have a favorite. I see there as being three big old-fashioned realistic traditions of trying to solve the measurement problem. One are hidden variables theories, of which the most successful example that we have so far, I think, is Bohmian mechanics. Another are collapse theories, of which I think the most successful example we have so far is the GRW theory. And then there are many worlds attempts. I do think that Bohm and GRW are both much more promising than many worlds, just because I have serious worries about whether many worlds can account for, has a good account of quantum mechanical probabilities. I worry that the various strategies for making sense of those probabilities, decision theoretic strategies, self-locating strategies, aren't going to work. So I have worries about Everett. Both collapse programs and hidden variables programs, that is GRW and Bohm, seem to me to be live options that continue to be very much worth studying and developing. We still, there are still questions about exactly how these theories are going to look in the context of relativistic quantum field theories or string theories. Of course, there are questions, as with any quantum theory, about how they're going to look in connection with gravitation and so on and so forth. But these still seem to me to be live programs that are very promising. Between the two, no, I certainly don't have a favorite. And indeed, these two are theories that are in principle going to differ in their observable predictions about how the world behaves. So in some sense, it's not up to us to decide between them. It's going to be up to experiment to decide between them. And of course, I'm always hoping that people will come along with a new proposal, with a different proposal. A possible new proposal is what I was talking about today. But yes, as things stand now, I wouldn't say I have a favorite. I would say that I am pretty pessimistic about Everett, but between the collapse tradition and the hidden variables tradition, I think these are both live traditions, viable traditions, and they need to be studied. They need to be studied both from the angle of further theoretical development and from the angle of testing them empirically.
So imagine, for the sake of argument, that all the realist options in quantum mechanics were somehow taken off the table, whether due to empirical inadequacy or internal inconsistency, what have you. If you were forced to retreat to a weak realist or even anti-realist way of thinking about quantum mechanics, which option would you find least objectionable?
That's a good question. I'm not sure I know how to answer. That would put us in a very different position than I take us to be in at the moment. That would, really have the feeling of pulling the rug out from under one. I'm not sure what I would think. I'm looking for what I hope for from physics is understanding. And what I have in mind when I speak about understanding is somebody tells me a story about what happens in a kind of realistic tone of voice. If that possibility is gone, it's hard to know what I would think. Maybe I would start choosing among various weakly realistic options or anti-realistic options, or maybe I would decide, gee, I'm disappointed in the whole project of physics. It's definitely true that what I'm hoping for from physics, what I've been hoping for since the beginning of my interest in physics, is that somebody is going to, in a fairly straightforward, flat-footed way, tell me the story of the world. And when I say tell me the story of the world, I have in mind some list of propositions that can be imagined to be the literal, objective, non-perspectival, old-fashioned, flat-footed, metaphysical truth. If that's really not available, that's going to be, to my mind, a stunning development. I don't know what I would think.
Sure. In your view, what are the three most important questions in the philosophy of physics, or in the philosophy of science more generally?
I mean, let me put it this way. The things that have always captured my interest is questions about whether the scientific project, as it was traditionally imagined, has limits, or whether it's going to. The way I got interested in quantum mechanics was precisely, and this relates to the previous question, was precisely because one heard, when I was growing up, that the old-fashioned realistic project of physics had fallen apart, had reached its limits when we go to subatomic particles. That the old project of realism, of course, there's a long history of philosophical critiques of realism, skepticism, underdetermination, all kinds of stuff like that. But the case of quantum mechanics was supposed to be different from all these. Here, the critique of realism was not coming from philosophy, it was coming from within physics. That in some sense, the physical project, as traditionally understood, had committed suicide, okay, in the context of quantum mechanics. That really interested me. I wanted to know if that was really true and how that could have been true. That is, I remember being puzzled by somebody said, you know, it seemed as if people were saying, look, because certain experiments came out in certain ways, because the pointer ended up pointing to the right as opposed to pointing to the left at a certain experiment, we had discovered that there couldn't be, that in some sense there wasn't an old-fashioned real world out there. How could that be? Okay. I was puzzled by how people could have thought such a thing. And indeed, the more I thought about it, the more I went into it, the more I studied what people had to say about it. It seemed to me that these declarations that the realistic project was over, were really about a lack of imagination, on the part of the people who were making these declarations. And that in fact, from before I was born, there had been theories around like Bohm's theory, which people just hadn't paid any attention to, that showed how the scientific project as traditionally understood, could go on. Similarly with the direction of time, what got me interested in the direction of time is, a widespread tradition in philosophy, particularly in continental philosophy, but also in the analytic tradition, of thinking that, the phenomenon of the temporal was somehow deeper down in the metaphysical structure of the world than physics was. There couldn't be a naturalistic account of that. This seemed to be another place where the scientific project was encountering its limits. And it's these moments, it's these situations in which it looks as if, or it's alleged to be the case, that the scientific project is encountering its limits that really intrigue me, that really interest me. So those are the kinds of philosophical questions that I get excited about.
Thank you. So we're actually running out of time, so I should turn to the question of time. Yeah. In my view, one of the most ambitious parts of your work would be the attempt to recover the manifest images of time, including the asymmetries found in various physical processes, of course, but also in memories,
Right.
causation,
Right.
intervention, and so forth, without relying on a primitive, temporal asymmetry.
Right.
So in your view, is there any aspect of the manifest image of time that still seems kind of resistant to such a reductive explanation?
At the moment, I don't see any obstacles there that look as if they can't be overcome with the right kind of thinking. It's definitely true that you start out with this ambitious project of naturalizing all this stuff, of reducing all this stuff to physics. And it is definitely true that that project hasn't always gone smoothly. And there have been interesting objections raised to it at various points. It's also true that at least case by case, um, um, I think people have been able to see an adequate response to each of these objections, but maybe if you pull back, that maybe begins to make the project look more shaky. So I don't know exactly what to say about this. We're very much in the middle of this project. It's at the moment, it's not the case that I can say, look, I can see something on the horizon, and I just have no idea at all how this project would deal with that. On the other hand, there are lots of specific objections. I'm not sure I know what the best response to each of those objections is. So no, I wouldn't say there's some particular alarm bell going off now, but there's a lot of work left to do on this project. The project has turned out to be more complicated than I originally thought it was going to be. We'll have to see what happens.
Can you take a couple of examples of
Yeah.
each project?
We had, people who were working on this had arrived at a certain way of evaluating counterfactuals. And it was pointed out by Adam Elga at Princeton that if you adopted that mode of evaluating counterfactuals, it could turn out in certain cases, suppose that the continent of Atlantis once existed, but there are no macroscopic traces left in the world of the existence of Atlantis. It turns out that if something like that is true, then you could argue that if I had snapped my finger a minute ago, which I didn't, then it would very likely to be true that Atlantis wouldn't have existed, okay? So by snapping my finger, I could have drastically changed things about the past, okay, counterfactually. That seems at first really bad news for this account of counterfactuals. On the other hand, if you think about this some more, um, the situation gets more complicated. This is true on this way of evaluating counterfactuals, but it's also true that the counterfactuals only come out this way in the circumstance where there is no macroscopic evidence at present of the fact that Atlantis ever existed. So if it were true that this depended on snapping my fingers, I could never know when that was true. I could never use that, to gain any practical advantage in any way or anything like that. So you think about this for a while and you say, well, maybe it's actually true that in very strange circumstances like that, the existence of Atlantis depended on whether or not I snapped my fingers now. This is one example of a way in which the project hasn't gone as expected, but then you think about it for a while and you say, well, maybe that's something the project can accommodate. There have been a number of objections like this. There were other objections, more elaborate forms of this Elga objection due to Matthias Frisch. Those required further readjusting of our understanding of what we were doing. So you start out by saying, okay, what we want to show from the laws of physics is that there can't be any large-scale effects on the past by acting in the present. After the Elga example, you say, okay, I take that back. There can be large-scale effects on the past as a result of what we do in the present, but they can't be the kinds of effects that we could ever know about or have any control over. So you find yourself constantly retreating a little bit, constantly modifying what it is that you think you want to prove. You have to keep in mind all the time that there shouldn't be any a priori ideas about what you want to prove. What you want to prove is that the fundamental laws of physics are adequate to explain our experience. Okay, so the project is ongoing. It keeps on stumbling and then getting back up. Do I see any obstacles at the moment that look really forbidding? Not that I can see at the moment, but somebody may tell me about one tomorrow.
Great. This is our last question. I assume that many philosophers and philosophy students are attracted to the foundations of physics questions, but they may also be intimidated by, understandably, its technical challenges and so on. So what is your advice for them?
Well, first of all, the first advice is not to be intimidated. I think the interesting questions in foundations of physics, at least so far, have been, have involved fairly simple fundamental physical questions. If you take a course in quantum mechanics, after 2 weeks, most of your time is going to be spent doing perturbation theory. Okay, that's not very relevant to the questions that concern us about foundations of quantum mechanics in philosophy of physics. Of course, as people undertake serious philosophical examinations of quantum field theory, so on and so forth, the discourse may get more technical, but it always turns out to be, if you just sort of close your eyes and jump into this stuff, it always turns out to be easier to learn it than you were afraid it was. But I certainly would recommend that people get as much physics training as they can. It makes things much easier. It's also the case that you don't want to be in debates with physicists where they just sort of pull rank on you because they can talk about technical matters that you're not familiar with. So the more physics you get under your belt, the better. But if you have a curiosity about this kind of stuff, if you have a taste for this kind of stuff, I tend to be very encouraging to people to jump into it.
Thank you so much, Professor Albert. It was a great pleasure and honor having talked with you. Thank you so much.
Thank you.
Have a good time in Korea.
Thank you very much.
Thank you.